So when we were talking about variables, we talked about there being different types of variables. For now, we're going to take a look at the numeric types, or the numeric data types, and then we have integers and longs. And there's two main types of, or categories of numeric data types, and that's integers and floating point numbers. Integers are whole numbers, and those are numbers that do not contain a decimal point. And we use integers to store, obviously things that are whole numbers. And so the two main versions that we use are ints and longs. And what's the difference between these two? Well, the amount of memory required to store each value. A long can store larger numbers, but requires more memory to store each value. For example, an int uses 32 bits to store its values, but 1 bit is used for signing, so we have 2 to the 31st power, which roughly equals plus or minus about 2 billion numbers, or up to 2 billion, 1 million, yada, yada, yada. In contrast, a long uses 64 bits to store its value, or double the amount of memory space required by an int, but it can store values up to 2 to the 63rd power. So that is a huge number, which is roughly, right there. -9 times 10 to the 18th up to +9 times 10 to the 18th. I don't even know what that is. I don't know what number you call that. Of course, you should be already familiar with ints because you've seen them already. But you should use the smallest data type for variables that will never need to hold a larger value. For example, if you are, say, writing a program that stores, I don't know, student information, chances are you're not going to need to have a long used to store the student IDs. You are never going to get into a case where you have a student ID number that is going to be that many digits long. If you do, let me know and you can come back and, tell you told me so. But in that case, you would only need to use an integer. And just as you saw how we had two types of variables to store integers and whole number values, we have two types to store floating point numbers, or numbers that can contain a decimal, and that's called a float and a double. And of course, to declare them, you simply precede the name of the variable with the type. So just like here, we have float GPA and double bank account balance. And similar to ints and longs, floats use the same number of bits to store information. Float uses 32 bits, and a double uses 64 bits. However, unlike ints and longs, using a double not only allows us to store a larger number, but it also allows us to store a smaller positive or negative number. And that sounds kind of confusing, but that means we can get greater precision after the decimal place. So here's a question, and take a minute to think about it. Would you use a float or a double for a GPA calculation? And what about a bank account? So to answer that question, the general recommendation is that you use a double rather than float as a standard. You don't use float variables where there's calculations involving money or scientific measurements. Those type of calculations really require the accuracy of a double, and floats aren't very accurate. Now with the GPA, generally you only need 2 decimal places, so that's fine. And you can store some really big values in floats and doubles, but just remember that you're not going to have the level of precision that you need to accurately represent big numbers. So a double will only hold 15 significant digits, while a float will only hold 6 significant digits. So that's important to remember when you're working with these numbers. You can store integer values in a float or a double as seen here. However, you can't do the reverse. All right, this will automatically get converted or casted to a double, Whereas in this situation, this will generate a compilation error, and it'll tell you, hey, we can't put 26.7 into an integer because integers are for whole numbers only. It won't truncate the decimal and won't get rid of it. It'll just give you a compile error. So that's bad. So this is the same thing, right? Don't do it. And another important concept when working with numbers is the concept of a constant. And a constant is a fixed value or a value that can't be changed during a program's execution. And examples of this include integer constants, floating point constants, and string constants. An interesting point is that the default type for an integer constant is an int, but the default type for storing a floating point constant is a double as opposed to the float. So it uses the smaller version when dealing with integers, and it uses the bigger version when dealing with floating point numbers. So just be aware of the difference between those two, that this is the standard default when representing an integer, and this is the standard value when representing a floating point number. So anytime you type in, say, 2.7, Java is automatically going to convert this to a double. So let's take an example or look at an easy gotcha problem. This code right here generates a compilation error. Where is the error and why? Go ahead and look at it and think about it. So if you look at the code, if you were to actually take this and put it into a program, you can see why it happens. So let's do that. So here we have our floating point test number. We're declaring this float called GPA and a float called miles per gallon, and we're setting these values to it. So what do you think is going to happen? Well, if we compile it, we're going to hit Control-1 to compile it. Boom! It exploded on us, right? It says, hey, I don't like this. Error. Incompatible types. Possible lossy conversion from a double to a float. And then same thing again with the miles per gallon. Well, remember, that's because Java uses doubles as its default. So this is a double, and we're trying to assign a double to a float, and that's not going to work. So if we want to make it to work, what we have to do is we have to tell the compiler, hey, this is a float, by adding an F to the end of the value. So if we do that and hit compile, look at that, magic, it works. So it now knows that this is no longer a double, it's actually a float, and so it allows the assignment operation to happen. So again, just to recap, some possible solutions is to always use double variables instead of float variables, or you can explicitly cast or convert the floating point number, or the double to a floating point number by adding an F or a capital F as a suffix, as we did here and as I showed you in the program. So there's some other stuff you need to know about constants. And so far we've only covered one type of constant, and that is a hard-coded constant. But there's also another type called a name constant. For example, you can see here that we have this value of 299,792 yada 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 is a hard-coded constant. But if we want to create another constant, say the speed of light, then we can create a name for it and have it be a named constant. So for example, you can see here we have final double speed of light equals this value that we have hard coded up here. So now instead of having to type out that value every time, all we have to do is we just have to say speed of light. And notice how the speed of light is capitalized. You can see here that it's part of the naming convention is that named constants are always all caps. And the compiler knows that speed of light is a constant because of this keyword final right here. This is what tells the compiler that this is in fact a constant, because what that final does is it tells the compiler that this speed of light value, once it's assigned a value or once it's initialized, cannot be changed. And if you try changing it later in the program, it will throw an error at you. So all constants, all named constants, will use the final keyword modifier. And then also, you should, again, do full caps for your constant variable name. Okay, so what happens if we try to change the value of a constant once it's been initialized? So you can see here we have the speed of light program that assigns a value to the speed of light up here. You can see right, let me get some ink. So right here we assign a value of about 300 million to the speed of light. And it runs and executes just fine. So what happens if we try to modify the program later to change it? So you can see down here we change the speed of light to say 100 meters per second, and then we try printing out the propagation delay. And when we compile it, you can see that it gives us this error down here, cannot assign a value to a final variable, and then it tells you where you're going wrong. So that's what happens if you try changing a variable that is a constant. It's going to yell at you, basically. So constants don't seem like they're all that exciting of a topic. So why am I wasting all this time? Well, there's two main benefits from using constants, and they're pretty important. The first is by using named constants, you'll write code that's ultimately more understandable and easier to read. But more importantly, if you ever need to change the value of the constant, you only have to do it one place. You initialize it at the top of your program, and then any time that the code is referenced later in the code, it will automatically be updated if you change it up at the top. If you use the hard-coded value of the speed of light and you type out the numbers every single time, if that number for whatever reason needs to change, so speed of light's a bad example, but if you have to type in the number, you're going to have to find and replace it over and over and over and over again. So that's why you should use a named constant, because then you can just update it in one place. And at this point in your education, you should be more than aware of the basic 4 arithmetic operators. Plus, minus, multiplication, division. But one that you may not be aware of is the modulus operator. And we're going to get to that in a bit. But the division operator depends on whether the operands, which is the things that are on either side of the operator, are integers or floating point numbers. So this is the operator, and then this would be the operands, right? So how Java handles the division operator depends on whether these are integers or whether they are floating point numbers. And so we'll take a look at that on the next slide. So when the Java Virtual Machine, or JVM, performs division on floating point numbers, it performs what we would call calculator division. We call it calculator division because Java's floating point division works just the same way as if you were to put it into a standard calculator. For example, if you divide 9.0 by 4.0 on your calculator, you get 2.25. So in this example, you see that exactly happens. So let's take a look at it in actual Java code. So here we have a program called Simple Math that simply takes two numbers, in this case floating point numbers of type double, and is going to divide them and print them out. So if we execute the program, drag it to where you can see it, you can see here that 9.0 divided by 4.0 is equal to 2.25. Okay, so what about if they're integer values? For example, here, we have an integer being divided by a floating point number as evident by the decimal value. The 2 point, you can see that right here. Okay. What do you think happens? Well, this is an example of a mixed expression. A mixed expression is an expression that contains operands with different types. Double values are considered to be more complex than integer values because double values contain a fractional component. And whenever there's a mixed expression, the JVM, that's the Java Virtual Machine, temporarily promotes the less complex operand type to the more complex type so that it matches, and so then the JVM applies the operator. So in this example, the 13 gets promoted to a double, and then the floating point division is performed. So this expression right here will evaluate to 6.5. So let's do that. Let's change this x to an integer, and we'll call it 13. And we'll have the second part be a double called 2. And then we'll go ahead and divide them. So we're going to compile it. And it compiled successfully, and we're going to run it. And you can see here 6.5, which is exactly what we got on the other slide. What happens if they're both integers? Well, let's make them both integers, and oops, get rid of our decimal there. Okay, nope, we want 2. And we're going to compile it, and we're going to run it. And you can see here that it does the integer version, and there's no remainder, no decimal. It just gives you the whole part of the number. So obviously 2 divided by 13, or 13 divided by 2 is 6.5, but we strip off this 6.5 because both, or the 0.5, because both values are integers. So like I said, there's 2 ways to perform division on integers. There's the traditional grade school version where you generate the quotient. For example, 9 divided by 2 is 4. The modulus operator also performs grade school division, but it does it and generates the remainder. So for example, 9 mod 2 is equal to 1, or 5 mod 15 is equal to 5. That's because 5 divided by 15 is 0 with a remainder of 5. So the modulus operator is used quite heavily in numbers of applications, and it's really useful for things like you can use it as a counter to count at only certain intervals. You can also use it, it's used quite heavily in cryptology, which is way beyond the scope of this lesson. But before you write it off as saying that the modulus operator is something that you're never going to use, you're going to use it quite a bit in your computer science career. In order to properly write computer programs, you need to have a good understanding of order of operations. So given this bit of information, or these initializations, use the operator precedence table in Chapter 3 to determine the result of the following expressions. So go ahead and pause it and figure it out. What you should have come up with is A is equal to 1.6 and B is equal to 6.0. Now, pause it again and see if you can write a program to check this. Or you can just wait and I'll demo it for you, but you really should try to do it yourself first. I'll wait. And you should have gotten something that looks like this. And of course, this is straight from the textbook of from the author. But you should have some class name followed by your main method, and where you initialize the values, and you simply just put it in like this. And if we run it, We're going to compile it, and then we're going to run it. And you can see here that, in fact, yes, the answer is 1.6 and 6.0. And we're going to do some exercises in class to reinforce this. So make sure you understand the order of operations and how to apply them in your program. So let's look at an operator that you may not be familiar with, and that's the increment and decrement operators. And they exist purely to make your life easier. You'll find that in programming, especially when working with loops, you need to add or subtract 1 to or from a counter of some kind. And these operators have shorthand notation that looks like this. You'll see a plus plus or a minus minus. And here is their equivalent expressions. You can see here we have a variable x, and it's being incremented. That is the same as x equals x plus 1. So this statement on the left is the same thing as the statement on the right. We can also do the same thing with the decrement counter, where we are subtracting 1 from a variable of some kind. Notice that we can also have the variable, the operator before or after the variable. In this case we have it after, in this case we have it before. And that's going to change the way that it's evaluated when you're using it in some kind of expression. For example, say you wanted to print out the value of x in some kind of loop, and then you want to increment the value. Well, if you have print, let me write it out here, print x plus plus, okay, and this is just pseudocode, this isn't actual proper syntax. What's going to happen if x equals 10, it's going to print 10 and then increment x to be 11. Okay? If you use the prefix notation where we have the increment operator first, plus plus x, what's going to happen is it's going to print out 11 because it is going to apply the operator before it's used in the expression, where the other way is it used the variable in the expression and then it applied the operator. So that's the difference between the postfix and the prefix notation on the operator. Let me erase this here. And then with Java, this is the preferred way of writing this type of operation. Anytime you need to add or subtract 1, use this type right here, or this type, doesn't matter, depends on what you need it for. But don't use these, because it's too long, it's not necessary, and the one on the left provides much cleaner code. In addition to increment and decrement operators, we can also use compound assignment operators to modify a variable's value. And we have them for all the major mathematical operations. So we have plus, minus, multiply, divide, and modulus. So this is how it works. It's similar to the increment operator, except for we're going to add, in this case, in the addition version, we are going to add 3 to the value of x. So this on the left is equal to the same thing on the right. So we are saying x is equal to x plus 3. Or in the bottom example, x is equal to x minus 4. So these two things are the same. So it's just a cleaner way of writing it, more concise. And again, style dictates that we use the compound assignment operators instead of statements like what you see on the right. So these are good, these are bad. Okay? So get used to thinking in those types of terms.